present a new multiplane computer-generated holography method that provides defocus blur similar to the natural light case by mitigating edge fringe effects in coherent systems. Rendering realistic-looking perspectives of a scene on a flat two-dimensional screen is possible today. Nevertheless, the actual illusion of perceiving three-dimensional scenes that match our experiences in real life is still beyond today's computer graphics and display technologies. There is a growing consensus in the industry and academia that computer-generated holography methods can emerge as the next-generation display technology. Here, you can see how natural light acts in the edges of defocus blur in natural viewing conditions. If we look at the one-dimensional plot of a small section of this transition, the intensity of the light beam maintains a smooth transition in the edge between white and black regions. This smooth transition provides the defocus blur that we are accustomed to see in real life. However, as computer-generated holography typically relies on lasers, defocused parts of a scene look unfamiliar for a human observer. You start to see high-frequency artifacts during the transition of edges. These are known as edge fringe artifacts in the literature. State-of-the-art algorithms suffer from these edge fringe artifacts and provides inaccurate defocus blur. We address these issues in the context of computer-generated holography used for multiplane reconstructions. Our method fixes these issues in the reconstructed images. Our optimizations start with an input image and a depth map. Our targeting scheme quantizes the depth map to the number of planes. Our final targets for each color channel contain in-focus and out-focus parts, whereas classical approaches render only in-focus elements. We claim this as our novelty. Here you see some sample target images from two different planes. Our targeting scheme is suitable for any optimizer in the literature, including the most common Gerchberg-Saxton method and stochastic gradient descent optimizers for holography. Most optimizers require a loss function to evaluate and improve the solutions. We also derive a new loss function that pays special attention to the focus parts and overall image integrity. As a result, we can derive an improved phase-only hologram for a given three-dimensional scene. We design and build a proof-of-concept holographic display to test our algorithms. Here you see our design layout with annotations. And here, you see our real-life prototype. Here we show the results of our optimizations using our proof-of-concept holographic display. We introduce a new loss function that helps computer-generated holography calculations when using either optimization or machine learning methods. We also introduced a new targeting scheme to set target images for multiplane image reconstructions. Together with the new targeting scheme, our loss function lets us mitigate edge fringe effects and helps us generate defocus blur that approximates incoherent illumination case while using coherent illumination. We establish a hologram generation pipeline for reconstructing multiplane images that uses a gradient descent-based optimization with a constraint inspired by the double-phase method. We implement a proof-of-concept holographic display prototype using a laser, a phase-only spatial light modulator, conventional optics, and optomechanical parts. We use this prototype as a base for real-life experimentation. Thank you for watching. If you stay, at the end of this video you'll be seeing more sample images from our holographic display.